Hi, welcome to Sachin Study Tech. Today topic is optimal binary search tree. You know already binary search tree, so can find out the optimal binary search tree. Given sorted array keys, so where frequency I is the number of searches for the key, construct a binary search tree for all the keys such that total cost of all the searches is a small as possible, the cost of the BST node is the level of the node multiplied by its frequency. The level of the root is 1. So here it is, for example, using recursion, the time complexity is big of n into 2 power n and space complexity is big of n. Using top down or bottom up approach by using dynamic programming method, the time complexity is big of n cube and space complexity is big of n square. So first, what is the binary search tree? You can discuss now. So binary search tree is a binary tree which satisfies some constraints. Left child contains values less than or equal to parent node, and right child contained values greater than the parent node. So what is the meaning of that? Now for example, you have the number of keys, key 10 and 20, 30, 40. So what is meant by binary tree? Binary tree is at most two childrens. The binary tree contains at most two childrens, that is 0 children, 1 children, 2 childrens. For example, what is the binary search tree? So here left child contains the value less than or equal to the parent node, right child contains the value greater than the parent node. For example, here there are 5 keys is there, so I am consider 30 is the root node. So what are the values are left side? Here it is 20 and 10 is the smaller, so left of it. Here 30, here it is, for example, I am consider the 40 and 50 is the right of 40. Here this is a binary search tree. For example, I am consider one more key, that is 35. So where it can, so 35 is there here, because you can compare with the root node. Here 35 is the greater than the root node, then go to the right side, here also can compare. So 35 is the less than the this node, then 35 here. So for example, here also I am consider another key is 25. So here 25 is less than the root node, then here 25 is greater than this, so 25 is here. So now for example, who are the keys 10, 20, 30 are the keys. How many binary search trees are possible for these keys? So what is the formula here? The formula is 2n cn by n plus 1. So that means, for example, here n is the number of keys, so 3 keys is there, that is 2 into 3, that is 2 into 3 c n. N means 3 keys is there by n plus 1, 3 plus 1, that is 4 keys, that is equal to 2 into 3 6 c3 by 4, that is equal to 6 into 6 factorial by 6 minus 3, 3 factorial into 3 factorial by 4, that is equal to, here it is, you can expand here, 6 factorial means here the 6 into 5 into 4 into 3 into here the 2 into 1, here it is 3 factorial, 3 into 2 into 1 and 3 into 2 into 1 by 4. So here it is 3 into 2 6, here 3 3 cancel and 2 2 cancel, 4 into here this 5 into 4, here the 4 cancel here, so 5. So here in these three keys 5 binary search trees are possible. 5 binary search trees are possible for these three keys. So this is the formula. So what are those? So here 10, here the 20 is greater than the root node, 20 here and 30 here. This is one tree. Another one is, for example, I am considered 20 as a root node, 20 here it is a 10, here it is 30, and also I am consider the 30 here, 30, and here it is 20, and left of it here it is 10, and also in root 30 I am considering here it is 10, here it is 20. Like that here also I am consider the root 10, here it is 30 and 20. So these are the 5 trees are possible. So what is the best binary search tree in this optimal binary search tree? How can find out? So for example, if you want to find the 10, so one comparison is needed. So this is the one comparison. Here it is, if you want to find out the 20, here it is one comparison, it is two comparisons, it is three comparisons. So I am considered this is the binary search tree 1 and it is 2, so it is 3. For example, here it is the fourth one and this is the fifth one. So 5 binary search trees. Here again comparison is, one comparison is needed. Here it is, for example, if you want to find out 10 is there in that tree or not, so it is one comparison. Here the second comparison, here also two comparisons, here 1, 2 and 3, here also 1 and 2 and 3, here also 1, 2 and 3. So you can see what is the average number of comparisons in this tree. 1 plus 2, that 3 plus 3, 6. 6 by 3, that is 2 here. It is 5 by 3, that is 1.6. Here it is 6 by 3, that is equal to 2. Here also 6 by 3, that is equal to 2. Here also 6 by 3, that is equal to 2. So what is the minimum number of comparison is there in that which tree? Here it is, this is the balanced binary search tree, so it requires the minimum number of comparisons. So what is the time complexity here? The time complexity of the binary search tree is big of log n. Space complexity of the tree is big of 1. So constant amount of extra space is needed for this. Now you can see, so this is the example binary search trees. So these are the, what is the optimal binary search tree in this? So this is the binary search tree. Thank you for watching this video.